we shall take the application of derivative to the next exercise where we have Rolle's theorem. What does a Rolle's theorem talks about? In a real valued function, the function should be real valued and f should be continuous in the closed interval a comma b. That's the first condition. F should be differentiable in open interval a comma b, and also f of a and f of b are equal. Then you will be able to find a number c in between a and b such that f dash of c is 0. Now let's try to geometrically mean this. Imagine I have a function which is real valued. That means I can sketch the graph of this function. First of all, you have 2 points. One point is a here, another point b here. Its corresponding y coordinates are f of a and f of b because the function is f. So let me denote this by a comma f of a and here b comma f of b. Now I need to sketch a graph joining a and b such that it should be continuous. So there should not be any break in the graph. It should be differentiable. Everywhere the slope of the tangent should exist. That means I should be able to draw the proper tangent at each and every point on the curve. So there are 2 possibilities. Remember, f of a and f of b are equal. That means the y coordinate here, the y coordinate here are equal. Then if I draw this graph, one possibility is I can draw the graph like this. Another possibility is I can draw the graph like this. Third possibility is I can draw the graph like this. But you will notice that however I draw this graph, there will be one point where the slope of the tangent would be 0. So here I can draw one tangent here and one tangent here where the slope of the tangent will be 0, because if you go up, you have to come down. Wherever the point you are going to turn, that point, the slope of the tangent will be 0. So I will be able to find at least one point C such that f dash of c will be 0 at this point. It may so also happen that I may have points like this, a here, b here, and I may have many points like this. Let's say the word at least. There exists at least one point. So here there are many points where the slope of the tangent would be 0. So like this, I will be able to find infinite number of points. I can find many points where the slope of the tangents can be 0. That's why the word at least one point is there. So here is my conclusion. The function should be continuous. That means there should not be any break in the graph. Function should be differentiable. That means everywhere the slope, I should be able to draw the tangents. Then, and there should be 2 points on the curve where the y coordinate should be equal. F of a and f of b should be equal. Then what I can do? Then I can find at least one point, either like this or like this. At least one point where the tangent will be parallel to x-axis, where the derivative will be 0. So you will, and what will be asked in the examination is, first is check whether Rolle's theorem is applicable for that particular function. When will be the Rolle's theorem applicable? It should be continuous, it should be differentiable, and thirdly, there should be 2 points where the function's value, that means the y coordinate, should be equal. Then you will be able to generate at least one point where the derivative will become 0. That's what the Rolle's theorem says. Our first question is, you need to check the validity of the Rolle's theorem for the following function. So I've taken the function f of x is x squared minus 4x plus 3. So first thing, what kind of function is this? This is a polynomial function, or in particular it's a quadratic function. We know that every polynomial function is continuous and differentiable in the whole domain. Therefore, there the domain they are given is 1, 3. So our first condition, we will say that f of x is continuous in closed interval 1, 3. Continuous is in closed interval because since f of x is a quadratic function. Again, second point, f dash of x, what is that? 2x minus 4. This is differentiable. F dash, this exists everywhere. There is no place where f dash of x does not exist. So it is f. Therefore, what you can say, f of x is differentiable in open interval 1 comma 3. Now we'll calculate the third condition, f of 1. F of 1 square minus 4 into 1 plus 3, which is 0. F of 3 square minus 4 into 3 plus 3. 9 plus 3, 12 minus 12, 0. So f of 1 and f of 3 are equal. Hence my conclusion is all the three conditions of the Rolle's theorem is satisfied. So if what is our question? Check the validity of the theorem. So this particular theorem, is it valid or not? We have checked. All the conditions are satisfied. Now we will find out its derivative. Where does the derivative become 0? So for that, I'm going to equate f dash x is 2x minus 4 to 0. So 2x is equal to 4. So x is equal to 2. Now, I have seen that f dash of 2 is 0. Now, check whether this 2 lies between 1 and 1 comma 2 belongs to 1 comma 3. So, we have found out a point in between 2 and 3, 1 and 3, that is 2, where the derivative becomes 0. And that's what exactly the Rolle's theorem says. Hence, Rolle's theorem is satisfied. So if this point where the derivative becomes 0 would not lie between 1 and 3, then we would have said Rolle's theorem would not satisfy. But Rolle's theorem says that we will be always able to find at least one point where the derivative becomes 0, and we have found out the point 2 where the derivative is becoming 0. Let's check the validity of this function, f of x equal to modulus of x minus 1 in the interval minus 2 comma 4. Now you know that modulus of x minus 1 is a continuous function. So for example, f of x is equal to x minus 1 if x is greater than 1 is equal to minus of x minus 1 if x is less than 1. That's the meaning of you can put equal to anywhere. So you will notice that this function is continuous when limit x tending to minus 1, limit x tending to 1 minus fx and limit x tending to 1 plus fx and f of 1 are equal. Therefore, f of x is continuous at x equal to 1. So I can say in the interval, so f of x is continuous at x equal to 1, hence continuous in closed interval minus 2 comma 4. But you know the derivative of f dash of x. F dash of x is 1 if x is greater than or equal to 1 and equal to minus 1 if x is less than 1. So f dash of 1 minus is not equal to f dash of 1 plus. So when x is little less than 1, f dash of x is minus 1. Little more than 1, it is plus 1, which implies f dash of 1 does not exist. If f dash of 1 is not existing, that means which implies f of x is not differentiable in the interval minus 2 comma 4, in the open interval minus 2 comma 4. So at 1 it is not differentiable. So although f of 1, f of minus 2 is how much? F of minus 2 is 3, f of minus 2 is 3 and f of 4 is also 3, but still the derivative, all the other two conditions are satisfied. Continuous, f of minus 2 and f of 4 are equal, but it is not differentiable in the interval. Therefore, I can say, therefore, the Rolle's theorem is not applicable. So, let's verify Rolle's theorem for the function f of x is sin x plus cos x plus 7 in the interval 0, 2 pi. First of all, sin x and cos x are continuous functions, are also differentiable functions. You know the graph of sin x and cos x, they do not have any break anywhere. Therefore, it is continuous, it is differentiable. If you do sum of two continuous and differentiable functions, it will be also continuous and differentiable. Therefore, I can say that first condition is satisfied. F of x is continuous in 0, 2 pi. Second, f of x is differentiable in open interval 0, 2 pi. That are the conditions of Rolle's theorem. Your closed interval, your open interval. Third, f of 0 is sine 0 plus cos 0 plus 7, which is equal to 8. F of 2 pi, that is sine 2 pi plus cos 2 pi plus 7, that is also 8, because cos 0 and cos 2 pi both are 1 and these both are zeros. Now, if the three conditions are satisfied, we should be able to find at least one point where the derivative becomes 0. So I'm going to find f dash of x. F dash of x is cos x minus sin x. Derivative of sin x, cos x, derivative of cos x minus sin x, derivative of 7, 0. So we have this much. Now I'll find out where f dash of x becomes 0. Implies cos x minus sin x equal to 0, which implies cos x equal to sin x, which implies tan x equal to 1. I divided by cos x, so tan x equal to 1. In the interval 0 to 2 pi, which are the point where the tan x becomes 1? We know that tan pi by 4 is 1. So tan of pi by 4 is 1. So this implies x equal to pi by 4. And x equal to pi by 4 is a number between 0 and 2 pi. So I am able to find f dash of pi by 4 equal to 0, and pi by 4 belongs to 0, 2 pi, open interval 0, 2 pi. Hence, the Rolle's theorem is verified. 2 points here. F dash of pi plus pi by 4. F dash of pi plus, that is f dash of 5 pi by 4 is also the tan x would be 1. So we have one more point. 5 pi by 4 also belongs to 0, 2 pi. Hence, we have 2 points where the derivative becomes 0. One is pi by 4 and other is 5 pi by 4 where the derivative becomes 0. Okay, let's look at the reverse problem. Rolle's theorem holds for a function. That means the function is satisfying the Rolle's theorem, but the function is not fully defined. There are two unknowns in the function. One is p and other is q. And the function is satisfying Rolle's theorem in 1, 3. And where the Rolle's theorem's point, where the derivative becomes 0, is 2 plus 1 by root 3. You got to find the value of p and q. So the first condition that we have, because Rolle's theorem is satisfied in 1, 3, f of 1 should be equal to f of 3. So you will get an equation with p and q using that. Then second condition will be the derivative at 2 plus 1 by root 3 would be 0. So from that you will get the second condition. So let me apply first condition. So 1 cube plus p into 1 square plus q into 1 plus 5 should be equal to 3 cube plus p into 3 square plus q into 3 plus 5. Let me cancel this constants. Then 1 plus p plus q is equal to 27 plus 9p plus 3q. So from here I can get an equation. P gives to 8p plus 2q is minus 26. So dividing by 2, 4p plus q is minus 30. This is my first equation. This is my equation number 1. Now I'll apply the derivative at c will be 0. So I'll calculate f dash of x. So f dash of x will be 3x square plus 2px plus q, your derivative. So f dash of 2 plus 1 by root 3, that is 3 into 2 plus 1 by root 3 the whole square plus 2p into 2 plus 1 by root 3 plus q should be 0. Now we'll solve this two equation. One we have 4p plus q is minus 13. Another condition we have like this. If you look at this, 2p into 2 you will get 4p. 4p plus q. You can easily understand here. When you open this bracket, I am getting 2p plus 2. This is 4p, and there is a q, and 4p plus q is minus 13. You will be able to replace that. So let me expand this. So I have 3 into 4 plus 4 by root 3 plus 1 by 3 plus 4p plus 2p by root 3 plus q should be 0. this implies. Now I will calculate the second part of it. I will use another color because I need to apply this. So I have 12 plus 12 upon root 3 plus 1. So I multiply 3 into 4, 3 into 4 upon root 3 and 3 into 1 by 3. Then 4p and q I will take together and 2p by root 3 over here. And that should be equal to 0. Now I can replace 4p plus q by minus 13 and 12 and 1 will give you 13. So 13 plus 12 upon root 13, root 3 plus minus 13 plus 2p upon root 3 is 0. Again I can get this 13 and minus 13 cancelled. Now my calculation became very easy. This is very important thing. This substituting 4p plus q as minus 13 should be done in the beginning. So now I can write this implies 12 plus 2p upon root 3 is 0. So from here 12 plus 2p is 0. So p is minus 6. Now if I replace p as minus 6, I can get q's value. So I'll go for the next condition. 4 into minus 6 plus q is minus 13. So q is equal to minus 13 plus 24. So q is equal to 11. So you have p is minus 6 and q is 11. So your answer is p is minus 6 and q is equal to 11. The second theorem that we have is known as Lagrange's mean value theorem. In short, we call it as LMVT. Both the Rolle's theorem and Lagrange's theorem both are called as mean value theorem. So this theorem is known as Lagrange's mean value theorem. In a Lagrange's mean value theorem and Rolle's theorem, the first conditions remains the same. First of all, the function should be real valued function. That means you'll be able to sketch them on a graph paper on a real plane. The function fx's should be continuous. And function should be differentiable, continuous in closed interval and differentiable in open interval, AB. But here there's no condition like f of a and f of b should be equal. That condition is so applicable in Rolle's theorem. Here no such condition. So let's try to find out what is the speciality of Lagrange's mean value theorem. Here I have x-axis and y-axis. And here the function graph y equal to f of x. One point A here, another point B here. The coordinate of this point is A comma f of A. The coordinate of this point is B comma f of B. I can draw a secant like this. A line joining, let's say, capital A and capital B. This is a secant. Then I will be always able to find a tangent to this particular curve which is parallel to this secant or this chord. So I am drawing that tangent. I'll draw that with a different color. So I will be able to find a tangent at the point C. I can find more than one point also. I'll be able to find at least one point C where the slope of the tangent and slope of this secant are equal. Let's find what the slope of the tangent at C. It is f dash of C. This is the slope of the tangent. Let's find the slope of the secant. y2 minus y1 upon x2 minus x1. That is exactly what we have written here. You will be able to find at least one point C where the slope of the tangent is equal to the slope of the secant. That is f dash of C is equal to f of B minus f of A upon B minus A. And that is what is known as Lagrange's mean value theorem. We need to verify Lagrange's mean value theorem for the function log x in the interval 1 comma e. So first of all, in 1 comma e, f of x is, log x is continuous. You know the log's graph, it is continuous. And the derivative of the log x also exists because the derivative of log x is 1 by x. 1 by x does not exist when x is 0. But you can see in the interval 1 comma e, log 1 by x is existing, so it is differentiable. So I can just directly state. Every time you have to just state it. We don't have to give much reason there. What is the statement we have to write? f of x is continuous in closed interval 1 comma e, then f of x is differentiable in open interval 1 comma e. You have to only just state it. If it is not differentiable, then probably you'll have to write out why it is not differentiable. But here log x is differentiable, so we have to only just state it. Now what Lagrange theorem says, I will be able to find at least one point C where f dash of C will be equal to f of B, that means f of E, minus f of 1 divided by E minus 1. So what is f of x here? Log x. What is f dash of x? F dash of x is 1 by x. So I will substitute now. F dash of C, 1 by C, is equal to f of E is log E, minus log 1 upon E minus 1. That is 1 by C will be equal to log E is 1 because the base of the log is E. So log E to the base E is 1. Log 1 is 0. So I get E minus 1. So taking the reciprocal, C is equal to E minus 1. Now we need to check whether is this number lies between 1 and E or not. You know that E is approximately 2.4. So E minus 1 is somewhere 1.4. So naturally E minus 1 will be a number between 1 and E. So E minus 1 will be a number between 1 and E. That implies LMVT is verified. LMVT is verified. So we have checked first, is it continuous, is it differentiable, and we found out the value of C, and we saw that C lies between 1 and E, and hence Lagrange's mean value theorem is verified. Let's try one more problem. Here is a function x minus 1 upon x minus 3. This function is discontinuous at x equal to 3, where the denominator becomes 0 is 3. So discontinuous at x equal to 3, but our interval is between 4 and 5. So 3 does not belong to that. So I can say the function is continuous in this. If I calculate the derivative of this, so denominator into derivative of the numerator minus numerator into derivative of denominator upon denominator square. So if I calculate this, x minus x will get cancelled, and I am getting minus 3 plus 3, so minus 2 upon x minus 3, the whole square. This function is also differentiable in the interval 4 comma 5. It is not differentiable at x equal to 3, but it is differentiable at all other points. Now we will calculate what we have to calculate. We should be able to find a number C between 4 and 5 where the derivative should be equal to f of b minus f of a upon b minus a. So I am going to say f dash of C should be equal to f of b. One before that I'll write two sentences. Hence, f of x is continuous in 4 comma 5. F of x is differentiable in open interval 4 comma 5. So two conditions. So conditions of LMVT is satisfied. So I should be able to find f dash of C such that f of 4 minus f of 5, or f of 5 I'll write first, f of 5 minus f of 4 upon 5 minus 4. F dash of C is minus 2 upon C minus 3 the whole square. Should be equal to f of 5. Let's replace f of 5 here. 5 minus 1, that is 4 upon 5 minus 3, that is 2. F of 4, 4 minus 1 upon 4 minus 3 divided by 5 minus 4. That became, okay, that from here I can say minus 2 upon C minus 3 the whole square should be equal to, this is 2 minus 1, it should be equal to minus 1. So minus and minus got cancelled. So 2 should be equal to C minus 3 the whole square. So this implies C minus 3 should be plus or minus root 2. So C's value should be 3 plus or minus root 2. Now we need to have the point C to be between 4 and 5. So naturally C minus 2 root 2. 2 root 2 is 1.4 which is, if you subtract it, it will go outside the 4. So naturally, C is equal to 3 plus root 2 belongs to 4 comma 5. So I am able to find 3 plus root 2 where the derivative is becoming equal to f of b minus f of a. Hence I can say the LMVT is verified. Therefore LMVT is verified. So remember that whatever the value of C that you are getting, there should be at least 1 point. Now we got 2 points where the derivative becomes 0. But one of the point is not between the intervals. So that point to be rejected. And the point which lies in the interval 4 comma 5, that should be taken. And since we can find a point, so whatever the theorem said is perfectly right. Therefore LMVT is verified.